Alright, so this is going to be for the overview of the respiratory system that he's going to cover here. So I kind of drew it all out because I had plenty of time here today, so I thought I'd just make a video kind of explaining some of this, and then maybe it'll hopefully hope everybody understand like the stuff that's coming up, because it gets quite a bit harder than just the first lecture here, first few lectures. Okay, so the big thing with the respiratory system is it's divided into two parts, or two divisions. You've got the upper respiratory system, and you got the lower respiratory system. So the upper respiratory system, its function is going to be to bring the air in, to draw the air in, to humidify it, warm it, so when it's freezing cold out, it's not harming us or freezing our cells. So we need to warm it, humidify it, and then also trap any kind of pathogens or particulates or anything bad that is going to be breathed in through the nose or through the mouth. Up in our nose, we have kind of specific ways we do that. So in our nose, which this is my terrible interpretation of the nose, we have our mucus cells that are constantly producing mucus, and our nose and our nares are very small, and they're actually designed that way or grown that way because they want to force air through a small area where it can come into contact with as much mucus as possible. So when the air hits the mucus, it can trap those small pathogens and particulates that are going to be damaging our lungs unless they get caught. So up to 10 micrometers and above is going to get filtered out by the mucus of the upper respiratory system. So when we get an upper respiratory system infection, it makes sense that like with a cold, you get all stuffed up and you can hardly breathe. This area is meant for a lot of resistance to begin with, so any excess mucus accumulation is definitely going to make it really hard to breathe. Okay, so going on, I'm not going to kind of list off the anatomy of the respiratory system because that's not too hard. But we go down, we're going to follow a particle of air going through the respiratory system. So we can come in through our mouth, we can come in through our nose and our nares, we can go to the nasopharynx, to the or through the oropharynx, and then we can go down through our trachea, through our vocal cords and all that good stuff, and that's easy to look off the lecture slides and find, so I won't go into that. But we go through down, and then we come to our first division, or our two main bronchi. Okay, so when we're breathing in air, we're bringing into the lungs and going through multiple different tunnels or divisions of piping that allows us to conduct air into the lungs. So we have two main bronchi, and then we call that our first generation, or our generation 0, or our generation 1, excuse me. Our generation 0 is our trachea, or our main bronchus. So for these first generations, a generation is just a term that's going to be used to describe when there's a branching off of some of the piping of the airway. So imagine a tree, and with a tree it has all different branches, and a couple main branches come off of the big main trunk. And on those branches there's going to be more smaller branches coming off, and off of those branches even more branches coming off. And then eventually we get off to so many branches where it begins to be just leaves coming off, very small twigs. And it's the same idea here, except instead of leaves coming off of twigs, we have alveoli coming off of our terminal bronchioles. Okay, so the main thing that's important with this is our generation through generation 10, and these are important to know what generations have what in them and what their function is. So generations 1 through 10, they're composed of mucosal glands, goblet cells, or globulate cells, and cartilage, connective tissue, smooth muscle, and ciliated epithelium. So this is going to be another area where particulates can be trapped in the mucus. And the cartilage is also there to keep it open, keep the airway patent, to keep it open and actually allow airway or air to pass through. It's also going to have connective tissue to hold it all together, smooth muscle, which is very important for bronchodilating or bronchoconstricting, and we talked about already our anaphylaxis reactions. So we know that the deleterious effects that this can have on our body if we too much bronchoconstrict in this area. And then after about division 10 or generation 10, we get to generation 11 through 19, where there's a lack of cartilage. So you no longer have that holding your airway open. So this area kind of only opens when you're breathing in, okay, or holding in a breath. And here we still have our ciliated epithelium, so we can still trap particulates and move them out. But we don't have that cartilage, and we still have smooth muscles. So this can also play a role in anaphylaxis, so constricting our smooth muscle cells. So it's worth noting that, and I think it's high yield to know that, the first 16 generations are called the anatomical dead space. So anatomical dead space just means that it's an area that doesn't have any alveoli It doesn't have any alveoli on it, and it's not going to participate in exchange of gases through the alveoli. So no actual respiration is going to be there. They're also known as the conducting zones because their entire purpose is just to get to airway to the smallest branches of the respiratory system in order for gas exchange to actually take place in those structures. All right, so after the 19th generation, we begin to get a lot of alveoli off of our little twigs, we'll call them, or terminal bronchioles. And we get our final last few generations here of generation 20 and generation 23, or branch 20 and branch 23. You have no smooth muscle or cartilage, and you only have elastic tissue. So elastic tissue is important in the lungs for a specific reason. And that's because when we're inhaling and exhaling, we have to be able to pull apart the lungs, pull them open, and then allow them to return back to a normal resting position. And we learned in histology that elastic tissue is very good at resisting that pulling force. So it can stretch like a bungee cord and then bounce right back to where it normally is. Okay, so that's our conducting zone and our alveoli. At the end of our terminal bronchiole, we call them, we have our respiratory unit. So our respiratory unit is where we actually have our alveoli. And these are going to actually conduct air through our terminal bronchiole. And there's going to be hundreds of alveoli on each one of these terminal bronchiole. And air can come in to them and pass through these specific cells, or type 1 cells of the alveoli. They're very flat, and since they're so flat, gases can readily diffuse through them. We know that in membrane transport, we went over that gases can easily permeate or travel through the plasma membrane. And on the other side of that cell is going to be a pulmonary capillary. And the pulmonary capillary is going to contain tons of red blood cells flowing through there, waiting to drop off its CO2 and pick up oxygen. And it's very important that this air be coming in is rich in O2 and more poor in CO2 than what our body is having in our pulmonary capillaries. Alright, so that's that. We'll go into a lot more detail on that in a little bit. But the flat cells, and then Also, on these walls of the alveoli, they're going to be made up of these cells that secrete surfactants. So those are type 2 cells. And along those type 1 cells, we're going to have this so that each time we breathe in, our alveoli is reinflated. So when it's deflated, it's going to look like this, and then it's going to go to something like this when there's a lot of air in it, right? Air's going to come into here and blow it up like a balloon. Well, if we didn't have this this substance called surfactant, which is basically lubricant, the lubricant of the respiratory system, the cells of the alveoli would stick together and would fail to come apart. So our surface tension, if we can call it surface tension, is so great that the air can't force it apart unless it has this lubricant there to allow it to slide open. Okay, so that's why we have those two types of cells. Also within the alveoli, there are going to be kind of channels between two different alveolar units. And these are going to be called the pores of Kuhn. The pores of Kuhn allow air to travel in between alveoli and mix. Bacteria can also move through there, and viruses, and infect their way through the lungs that way too. So it's just kind of a cool anatomical space that also has a couple uses that we'll get to later. All right. So in our big picture of the lungs, we've got 2 lobes on our left side and 3 lobes on our right side. And the reason we have 2 lobes over here is because we got to leave space for our heart right here in the middle. Remember, it's more on our left side. And I was talking earlier about the mucosal glands and the ciliated epithelium of our upper respiratory system and our bronchioles, okay? And I said that it caught a lot of particulates. Well, there's something worth mentioning here, is what do we do with those particulates once we got them? We can't just leave them there stuck to the mucus inside of our lungs. That would be really bad for us. We're not solving anything doing that. So what our body has devised, which is kind of ingenious, is an elevator. It's an elevator to take the mucus out. Where's the elevator to? It's up and out of the bronchi, through the trachea, and back here to the esophagus, where we can go ahead, and this is kind of going to be a bad drawing, we can go ahead and dump that mucus to the esophagus down the throat, and it'll land in your stomach. And that acid, we know, is really harmful to bacteria, kills them all. So it does us a big favor by getting rid of all of our nasty, disgusting mucus that's built up within our lung cells. Okay, so how does it do that? It's got cilia on the epithelial cells. Those cilia have a specific beating pattern. They beat up. They're constantly beating up, and they're picking up that mucus, and they all work together to keep forcing things up, up, and up, until they reach the back of the throat, and you can dump it down the esophagus. It's kind of an ingenious system, right? And if you ever want to understand this better, the easiest way to actually see it in action, eat some ice cream, I promise you. So a lot of people don't realize when they eat ice cream that after a little while of eating it, they'll start coughing, or after they're done eating it, they'll start coughing. I always do, and I always wondered why that was, and it's actually because of our anatomy and because of the temperature of the ice cream. So when we eat ice cream, it goes down our esophagus, right? Well, our esophagus is right behind, or posterior to, our trachea. And as it's going down, it cools down our esophagus, and thus it cools down part of our trachea. In cooling cells down, we always know that the body wants to have a homeostatic temperature of 98.6. When it cools down, the cilia become paralyzed, and they can't beat upwards and keep moving mucus. like they normally would be able to. It's only temporary, thank God, but what happens is we get the effect of our body senses that we can't, or we are building up our mucus, which would normally be dumped to the back of our throat. So we got to get it out some way. The cilia aren't doing it, so we cough to get it out. Kind of an interesting fact. All right, so let me see how I'm doing on time here. Oh wow, that was 16 minutes already. All right, so we've got our general overview of the respiratory system. Now, in our lungs, we are going to have a pressure of about 760 millimeters of hydrogen. So that's an important measurement, but it's not too hard to understand why, because 760 millimeters of hydrogen is equal to 1 atm, or 1 atmosphere of pressure. So it's just our atmospheric pressure that's in our lungs. In between our lungs and our thoracic wall, we actually have something very, very important. It is our pleural space, and it is lined by our visceral and parietal pleura. Okay? And this space makes it so that the lungs actually never come into contact with the thoracic wall, which is important because it'd be very hard to move your lungs in and out if they were just attached to your actual thoracic wall. So we have a little bit of space in between the thoracic wall, which I've kind of depicted here, and our lungs. And that's called the parietal space, or pleural space, excuse me. And the way that it keeps the lungs kind of glued, not quite, to the thoracic wall is that it's under negative pressure. Let me make sure I'm still doing good on time. Yep. It's under negative pressure, and the way that it's under negative pressure is that it is just 4 millimeters of hydrogen, so 756 millimeters of hydrogen lower in this space than it is this space. But that is an important distinction, because from Boyle's law, we understand that, and the entire respiratory system is going to operate off of Boyle's law, so fair warning, it's going to be a lot to learn. Boyle's law basically states that, going back to freshman chemistry, our volume, as it decreases, our pressure increases, or vice versa. So as our volume increases, our pressure decreases, okay? And if we manipulate the space between our thoracic wall and our lungs, it's going to increase or decrease the volume of this space and thus pull the lungs open or collapse them down. So I've kind of got a syringe here to demonstrate that a little bit. So a cool way to understand Boyle's law and the way that it pertains to the lung is take a syringe, put your finger over it, put a little bit of air into it, as we can see there. Put your finger over it so that you're not letting any air from the outside in. As we pull down, you see we can pull down, but it's kind of going to jump back to the exact spot that it opened up from. So when we increase our volume, it's going to want to get back to the original volume that it started at because of our negative pressure. So our lungs are going to follow in the negative pressure of the parietal or the pleural space and going to expand or contract as needed. So this is actually a pretty important system. It's under really tight regulation, and I'm going to do a part 2 video that's going to explain it and how it's regulated, and then we're also going to go into some lung volumes and some pathologies here.